Stop perky just to start it. Pop 2 ghosts of purple just to stop perky just to start it. Pop 2 ghosts of purple just to stop perky just to start it. Pop 2 ghosts of purple just to stop perky just to start it.
The effect of auto-regulatory progressive house music on The effect of auto-regulatory progressive resistance exercise versus linear periodization on strength improvement in collegiate athletes. The effect of auto-regulatory progressive resistance exercise versus linear periodization on strength improvement in collegiate athletes. Journal of Strength and Conditioning Research 24/7, 17/18 through 17/23, 2010. Auto-regulatory progressive resistance exercise, APRE, is a method by which athletes increase strength by progressing at their own pace based on daily and weekly variations in performance, unlike traditional linear periodization, LP, where there is a set increase in intensity from week to week. The study examined whether 6 weeks of APRE was more effective at improving strength compared with traditional LP and Division I collegiate football players. We compared 23 Division I collegiate football players, 2.65 plus or minus 0.8 training years, who were trained using either APRE 12 or LP 11 during 6 weeks of preseason training in 2 separate years. After 6 weeks of training, improvements in total bench press, 1 repetition maximum, 1 RM, squat 1 RM, and repeated 225-pound bench press repetitions were compared between the APRE and LP protocol groups. Analysis of variance, ANOVA, and analysis of covariance, and COVA, were used to determine differences between groups. Statistical significance was accepted at less than or equal to 0.05. Autoregulatory progressive resistance exercise demonstrated greater improvement in 1 RM bench press strength, APRE 93.4 plus or minus 103 newtons versus LP negative 0.40 plus or minus 49.6, and COVA of 7.1, P of 0.02. Estimated 1 RM squat strength, APRE 192.7 plus or minus 199 newtons versus LP 37.2 plus or minus 155 newtons. ANOVA F equals 4.1, P equals 0.05, and the number of repetitions performed at a weight of 225. APRE 3.17 plus or minus 2.86 versus LP negative 0.09 plus or minus 2.4 repetitions, and COVA 6.8, P 0.02 compared with the LP group over a 6-week training period. Our findings indicate that the APRE was more effective than the LP means of programming and increasing the bench press and squat over a period of 6 weeks. Keywords: resistance training, strength and conditioning football. For decades, strength improvement has been a goal for the athlete attempting to secure a competitive advantage over the competition. The ultimate goal of any strength training program must be to deliver the greatest gains in strength to optimize athletic performance. For the exercise scientist and strength coach working with the athlete, determining the most effective program for eliciting maximum strength gains should be a primary focus. There is no universally agreed on approach to maximize strength gains in the athlete, but most coaches do agree that there needs to be a planning or periodization of training stimuli. Periodization is a programmed manipulation of several key training variables: rest, overall training volume, sets per workout, repetitions per set, intensity of training, and training frequency. Throughout a training cycle, periodization can be traced back to Saley's work on stressors and adaptation. Saley theorized that the body will adapt to meet the demand of stressors on the system, which has led to the specific adaptations to imposed demands, SAID principle. The theoretical product of integrating the SAID principle with the progressive overload principle implies that the athlete's strength will be gradually adapt to a steady increase in the intensity and volume of training. In simple terms, the muscular and nervous system adapt to meet the needs of lifting an increased load, requiring that loads continue to increase for strength to improve. Classic linear periodization, LP, is a breakdown of macrocycles, mesocycles, and microcycles in which intensity gradually increases and volume gradually decreases within and between cycles. Studies have shown that periodized programming elicits better gains in strength and performance than non-periodized programming. However, it is currently not clear what type of periodization is most effective. Daily undulating periodization has been found to be more effective than LP in some studies, even with equated volume and intensity of training. A less common and understudied form of periodization is autoregulation of training. Autoregulation is a form of periodization that adjusts to the individual athlete's adaptations on a day-to-day or week-by-week basis. This type of periodization allows the athlete to increase strength at their own pace by catering the program to the athlete's individual strength and performance on a daily basis. Because individuals increase strength or respond to training stimuli at different rates, it is possible that the use of autoregulation may maximize the amount of strength gained over a training cycle. A specific autoregulatory program derived from the original Delorme progressive resistance exercise (PRE) system and outlined by SIF is the autoregulation progressive resistance exercise (APRE) method. To our knowledge, no studies have compared strength gains elicited by a traditional LP program versus an APRE protocol. The purpose of this study was to compare the effect of an APRE training program versus a traditional LP training program on strength improvement in National Collegiate Athletic Association NCAA Division I football players during a 6-week off-season program. We hypothesized that an APRE program that adjusts to the day-to-day variation of performance capabilities would result in larger strength gains in previously strength-trained individuals compared to a program employed the traditional LP method. Methods: experimental approach to the problem. The goal of this investigation was to compare the effects of APRE to LP in strength-trained collegiate athletes. The primary dependent variables in this study consisted of bench press 1RM, estimated squat 1RM, and the 225-pound repeated bench press test. All dependent variables were obtained after the off-season, January through May, spring conditioning program baseline, and after the preseason, June-July conditioning program post. Subjects: we compared 23 Division I collegiate football players who were trained using either APRE 12 or LP 11 for 6 weeks of resistance training during the preseason conditioning program at the University of Missouri in 2 separate years. Demographic characteristics of each group can be seen in Table 1. All subjects had previously performed the LP program in previous training cycles. The LP group consisted of athletes who were trained using the 2004 off-season, whereas the APRE group consisted of athletes who were trained the following year, 2005 off-season, using the new training method. All athletes had similar training histories, see Table 1, were trained during the same time period in consecutive years, and were trained by the same training staff, which limited seasonal variability or differences in application of the programs. We sought to determine which of the 2 6-week training programs resulted in the greatest increase in estimated 1RM, 1 repetition maximum, bench press strength, estimate 1RM squat, and the 225-pound bench press repetition test compared with their final off-season spring results. Their retrospective analysis of human subject data was approved by the University of Missouri Institute Review Board. Auto-regulating progressive resistance exercise and linear periodization protocols. In this study, APRE was implemented for the bench press and squat exercises over the 6-week training period. APRE used 3 protocols: a 10RM program, a 6RM program, and a 3RM program. For each program, subjects performed a set number of repetitions at a certain percentage of 10RM, 6RM, and 3RM based on Delorme's PRE pre-program. Each of the 10RM, 6RM, and 3RM resistance training protocol consisted of 4 sets each. The 6RM program will be described here because it was the one that was used for the greatest portion of the study. During set 1, subjects performed 10 repetitions at 50% of the anticipated 6RM. During set 2, subjects then performed 6 repetitions at 75% of the anticipated 6RM. Finally, during set 3, subjects performed as many repetitions as they could at 100% of the anticipated 6RM until they reached failure. The weight used during set 4 was based on the performance during the third set using the adjusted table, see table 2. During set 4, repetitions were performed until failure, and the number of repetitions and load used were then used to determine the initial resistance for the following week's training. The LP group began the resistance training protocol with sets of 8 at 70 RM and worked up to a 5 RM by moving up a weekly predetermined percentage of the repetitions required. For the squat, 3 sets of 8 repetitions at 70 RM, 1 RM were performed during week 1. 4 sets of 6 repetitions at 75%, 1 RM were performed during week 2. 4 sets of 5 repetitions at 80%, 1 RM were performed during week 3. And 4 sets of 5 repetitions at 85%, 1 RM were performed during week 4. Maximal strength testing was then performed on week 5. For the bench press, week 1 was 3 sets of 8 at 70%, week 2 was 4 sets of 6 at 75%, week 3 was 4 sets of 5 at 80%, week 4 was 4 sets of 5 at 82%, week 5 was 4 sets of 5 at 85%, week 6 was the test. For the bench press, 3 sets of 8 repetitions at 70%, 1 RM were performed during week 1. 4 sets of 6 repetitions at 75%, 1 RM were performed during week 2. 4 sets of 5 repetitions at 80%, 1 RM were performed during week 3. 4 sets of 5 repetitions at 82%, 1 RM were performed during week 4. And 4 sets of 5 repetitions at 85%, 1 RM were performed during week 5. Maximum strength testing was then performed on week 6. Training protocol. This study examined whether APRE was more effective at increasing upper and lower body strength compared to LP. To our knowledge, no study has been done comparing APRE to LP among football players at a major Division I college football program. There was no attempt to match volume and intensity of training between the two protocols, as the volume and intensity of the APRE were set each day and weekly by the individual's performance. Both groups were a part of the same program and underwent the same demands related to off-season conditioning and sport-specific drills. In addition, athletes in both groups performed very similar resistance training programs and exercises, both performing a very heavy barbell bench at above 85% 1 RM 1 session per week, a heavy dumbbell bench press 1 session per week with 3 sets of 6 repetitions, and the 225-pound multiple repetition bench press 1 season per week. For the lower body, both groups performed squat exercises 1 session per week, front squat exercises 1 session per week, step-ups 1 session per week, lunges 1 session per week, glute hamstring raises 1 session per week, and Romanian deadlifts 1 session per week. The LP group increased intensity from 70 to 85% of 1 RM over the course of the cycle, whereas the APRE group performed the APRE 6 RM protocol with the appropriate daily and weekly adjustments to their training resistance. Testing. Subjects participated in their normal strength conditioning program for the off-season. There was no pro-testing or pre-testing or baseline measures taken before the initiation of the APRE and LP programs during the preseason, because this was not standard practice of the football program at the time. Rather, post-training LP or APRE strength values obtained at the end of the preseason training cycle, June-July, were compared to the strength values obtained at the conclusion of the previous off-season training cycle, January through May. Bench press. Maximum bench press was an estimated 1 RM based on 5 or fewer repetitions to failure. The 225 bench press repetition test was done to determine the number of repetitions that 225 could be successfully completed, a protocol commonly used by the National Football League scouts to determine strength. For both measures of bench press, the athletes were expected to start the lift from full arm extension, touch the chest with the bar, and then return the bar to full arm extension for the repetition to count. In addition, it was expected that the glutes remain in contact with the bench during the entire repetition. Repetitions that did not meet these two qualifications did not count in the final score. Squat. The squat maximum was an estimated 1 RM based on 5 or fewer repetitions to failure. The squat depth was determined by descending to the point of the hip joint being even with the knee joint and returning to the standing position. Statistical analysis. Change scores for bench press and squat strength were calculated by subtracting the off-season baseline value from the preseason post value, and change score was used as the dependent variable in the analysis. Independent samples, T-tests, were used to determine differences in baseline strength before training. T-tests were also used to determine demographic differences between groups. One-way analysis of variance ANOVA was used to determine differences in the improvements on bench press, squat, and the bench press repetition test between groups using SPSS V5 15 Chicago, Illinois, when statistically significant differences existed in baseline strength values. One-way analysis, or covariance, and COVA, was employed using the baseline value of the covariant and change scores as the dependent variable. Statistical significance was accepted at less than or equal to 0.05. Results. All data were expressed as means of plus or negative SD. The subject's characteristics, including age, weight, height, and training history, are listed in Table 1. There were no significant differences between any groups for any of the subject characteristics. There were differences in bench press strength, APRE 1,314 plus or minus 112, and LP 1,510 plus or negative 118, and T negative 2.9, DF equals 21. P is less than 0.01, and repeated bench press strength, APRE 9.9 plus or minus 4.2, LP 15.3 plus or minus 5.9, and T equals negative 2.6, DF equals 21. Excuse me. Between the APRE and LP groups at baseline, there was no difference between groups in squat strength. APRE 1,922 plus or minus 357 Newton, LP 2,112 plus or minus 230 Newton, and T is equal to negative 1.5, DF 21, P is equal to 0.15 at baseline. Pre to postseason changes in absolute bench press and squat strength were compared between the APRE and LP trained groups. Autoregulatory progressive resistance exercises demonstrated greater improvement in 1RM bench press strength. APRE 93.4 plus or minus 403 Newton, LP is negative 0.4 plus or minus 49.6 Newton, and COVA F equals 7.1, P is equal to 0.02, figure 1A. An estimated 1RM squat strength, APRE 192.7 plus or minus 199 Newton versus LP 37.2 plus or minus 155 Newton, and NOVA F equals 4.1, P is equal to 0.05, figure 1B. Compared with the LP group over the 6-week training period. The 225-pound bench press repetition to fatigue test was also measured to determine which program would have the greatest effect in improving strength endurance. Autoregulatory progressive resistance exercise demonstrated greater improvement in the number of repetitions performed at a weight of 225 pounds compared with LP, APRE 3.17 plus or minus 2.86 versus LP is equal to negative 0.09 plus or minus 2.4 repetitions, and COVA F equals 6.8, P is equal to 0.02, figure 1C. Over the 6-week training period, indicating that the APRE was also more effective than LP in increasing upper body strength endurance. Discussion. This study was one of the first to compare the effects of APRE to LP, and certainly the first to compare these training programs among NCAA Division I football players in a major university program. Autoregulatory progressive resistance exercise was found to be more effective at improving bench press strength, squat strength, and upper body endurance in previously strength-trained Division I athletes over a 6-week period compared to LP. These findings provide strong evidence that autoregulation of training may be important to consider when choosing a program to elicit maximum gains in previously trained athletes. Programs to systematically improve muscle strength were first described in the research literature by Delorme, who developed a method known as progressive resistance exercise, PRE, to progressively overload the quadriceps to improve strength after femoral fracture. Knight et al. Modified the original Delorme PRE program for rehabilitation of quadricep strength after knee surgery and developed a daily autoregulated progressive resistance exercise, or DARP. DAPRE, D-A-P-R-E, for DAPRE, the principles of PRE were used to determine the appropriate resistance for 2 sets of 5 to 7 repetitions. A third set was then used to determine a training load during the fourth set, and the fourth set was used to determine the training loads of the following week. This method demonstrated improvements in quadriceps strength compared to traditional methods. Autoregulation progressive resistance exercise used in the present study varies slightly from DAPRE, but also the rationale is similar. Autoregulatory progressive resistance exercise has 2 working sets, followed by sets adjusted according to individual daily variations of strength and performance, like PRE, DAPRE, and the goal of APRE is to work towards a repetition maximum. The difference between APRE and other protocols, and the difference within APRE protocols itself, is that they are designed for different training needs. There is an APRE 3 repetitions for strength and power, an APRE 6 for strength and hypertrophy, and an APRE 10 for hypertrophy. Delorme's PRE only had the original 10 RM protocol, and the DAPRE evolved to a 6 RM protocol. The present study focused primarily on APRE 6 protocol for strength and hypertrophy because these are the favorable adaptations wanted in collegiate football player. Although APRE has not been compared to LP previously in the literature, Stone and Herrick compared progressive overload training, of which APRE is one type, to LP. The researchers reported that there was no significant differences in strength between the progressive overload group and the LP group in untrained women at the conclusion of a 15-week study. However, the LP group continued to gain strength, whereas the progressive overload group appeared to reach a plateau in their strength gains. These findings led the research to theorize that LP might be a better method to use a yearly plan. However, the strength improvements observed during short-term APRE training, 6 weeks, in the present study conflicts with these findings from Stone and Herrick. The discrepancy may have been because of the benefits of the autoregulation of PRE used in this method on highly trained individuals versus untrained individuals. The discrepancy may have been because of the benefits of the autoregulation of PRE using this method on highly trained versus untrained individuals. Flexible non-LP is a similar type of programming as APRE, and it has been proven to be a successful approach among collegiate athletes. However, in flexible non-LP, the practitioner makes daily choices about the athlete's status and workout basis on the demands that will be placed on the athlete for that given day. For example, a day in which a training session occurred after a 3-hour practice with heavy loads of conditioning would require a different strength training workout than a pre-practice strength training session. Flexible non-LP allows adaptation by the coach or practitioner based on demands of stressors such as an increased conditioning or periods of increased competition. APRE, on the other hand, allows adaptation of a particular workout by the individual athlete based on their abilities for that particular day. The mechanism behind the effectiveness of APRE are not known. However, it could be that the greater strength gains resulting from APRE were because of a consistent adjustment of repetitions. It has been postulated by the experts in the field when it is a constant training protocol is used over a period of weeks to months that the body begins to adapt, leading to reduced effectiveness. Autoregulatory progressive resistance exercise training prevents this adaptation because the repetitions are used to govern by the athlete's ability on what that given day and will change from set to set and week to week. Theoretically, the athlete could continue a typical 6-week training cycle and never repeat the same repetition and intensity scheme throughout the entire cycle. This also fits with the theoretical basis of undulating periodization, as workouts use a repetition maximum that would not only vary from week to week but within the workout. Undulating periodization has shown effectiveness at improving strength. For example, Rhea et al. Found that by alternating the RM trained in each workout, strength was improved to a greater degree than by changing the RM every 4 weeks. Rhea et al. Also reported that undulating periodization was more effective at improving endurance. The variation in repetitions from set to set and week to week allow APRE training to work like undulating periodization, which could explain its effectiveness. There were several limitations to the study. First, the study was not set up as a traditional pre-post design and therefore has a methodological limitation. However, the novel aspect of the study is the application of these training protocols on strength trained NCAA Division I collegiate football players at a major Big 12 program. Because the football program was so structured in its off-season and preseason agendas, obtaining baseline measures of strength before the implementation of APRE and LP was not possible. We believe the findings, however, are intriguing enough to warrant future evaluations of the benefit of APRE in competitive athletes. Second, the generalizability of these findings is limited to strength-trained competitive athletes. However, the benefit of APRE would likely be most applicable to the trained population. Finally, there was no way to completely equalize the volume and intensity of training between APRE and LP, so it is possible that any differences could be contributed to differences in strength observed in the study. This is the first study to examine the effectiveness of APRE compared to LP in trained Division I collegiate football players. The data from our study suggests that the APRE protocol elicits greater strength gains than linear periodization programs in terms of the bench press strength, squat strength, and bench press endurance. It is reasonable to conclude from these data that additional strength performance other than bench press and squat would likely benefit from this type of training, although future studies are warranted. The practical applications. Because of the short duration of typical off-season and preseason programs, it is critical for strength coaches to achieve maximal gains in strength in as short a term as possible. It has been theorized that progressive overload training such as the PRE and APRE might be an excellent tool for shorter training periods. Typical of preseason or off-season training cycles, we recommend using the APRE method of training in highly trained athletes with greater than 2 years of previous training during short 6-week training cycles because it appears to be more effective than LP in improving strength and strength endurance gains. For the strength coach or practitioner who must demonstrate the greatest strength gains during short duration training cycles, APRE training is effective. Muscle activity during functional coordinating training, implications for strength gain and rehabilitation. National Research Center for the Working Environment, Copenhagen, Denmark. Department of Exercise and Sport Sciences, University of Copenhagen, Copenhagen, Denmark. And Research Unit for Musculoskeletal Function and Physiotherapy, Institute of Sports Science and Clinical Biomechanics, University of Southern Denmark, Odense, Denmark. Abstract. Muscle activity during functional coordination training, implications for strength gain and rehabilitation. Journal of Strength Conditioning Research 24/7, 1732 through 1739, 2010. The purpose of the study was to evaluate if different types of body positions and levels of progression of functional coordination exercises can provide sufficiently high levels of muscle activity to improve strength of the neck, shoulder, and trunk muscles. 9 untrained women were familiarized with 7 functional coordination exercises 12 times during 4 weeks before testing. Surface electromyographic EMG activity was obtained from rectus abdominis, erector spinae, obliquus exterminus, and trapezius during the exercises with 2 through 4 levels of progression. Electromyography was normalized to the maximal EMG activity during maximal involuntary contractions, and a p-value of less than 0.05 was considered significant. All record muscles reached sufficiently high levels of activity during the coordination exercises for strength gain, greater than 60% of the maximum EMG activity. Type of exercise played a significant role in the attained muscle activity. Body position during the exercises was important for the activity of the erector spinae, and level of progression was important for the activity of the trapezius. The findings indicate that depending on type, body position, and level of progression, functional coordination training can be performed with a muscle activity sufficient for strength gain. Functional coordination training may therefore be a good choice for prevention or rehabilitation of musculoskeletal pain or injury in the neck, shoulder, or trunk muscles. Introduction. Muscle strength is important for the longevity of life without pain. Furthermore, strength training can be effective as treatment and prevention of musculoskeletal pain. Besides muscular strength, improved coordination skills may be critical for prevention of musculoskeletal pain. Persons with musculoskeletal pain are observed to have an impaired coordination compared with healthy control. Therefore, coordination exercises are generally recommended for preventing and reducing musculoskeletal pain. The main advantage of functional coordination exercises is that several muscle groups are simultaneously activated, reflecting the muscle activity pattern during daily work tasks, and might therefore function as a preventative strategy towards work-related pain. Moreover, the high muscle activation with less stress on joints and muscles during functional instability exercises is generally considered beneficial for general musculoskeletal health and rehabilitation. However, a limitation of functional coordination training is a lack of increase in muscular strength. If coordination training can be performed with sufficient intensity to also induce a strength gain, this may further enhance its value compared to other types of prevention and rehabilitation exercises for musculoskeletal pain and injury. A muscle activity level of 60% of maximum voluntary activity is generally considered necessary for gaining strength. Although a high level of muscular activity can be easily attained during traditional strength training by enhancing the external load, it is not so easily achieved during complex functional coordination exercises and conventional therapeutic exercises. This may explain the lack of strength gain from functional coordination training in previous studies. The muscle activity during functional coordination training can mainly be modulated by voluntary activating the muscles more intensely for changing body positions or by applying higher levels of difficulty progression in each exercise. However, activity of the neck, shoulder, and trunk muscles remain to be studied during different types of body positions and levels of progression of functional coordination exercises. The aim of this study was to evaluate if different types of body positions and levels of progression of functional coordination exercises can provide sufficiently high levels of muscle activity to improve strength of the neck, shoulder, and trunk muscles. The hypothesis of the study were that the type of functional coordination exercises is important for the attained level of activity in the neck, shoulder, and trunk muscles, where some exercises evoke sufficient levels of muscle activity for strength gain, and B, the body position and level of progression of the functional coordination exercises are important for the level of activity in trunk, neck, and shoulder muscles. Methods. Experimental approach to the problem. For testing the hypothesis of the study, the activity in the neck, shoulders, and trunk muscles was recorded by surface electromyography, EMG, during functional coordination exercises of different types, body position, and levels of progression in women with musculoskeletal symptoms familiarized to these exercises. Subjects: 9 sedentary, untrained female workers, mean age 46 plus or minus 2.4 years, height 167 plus or minus 1.5 centimeters, weight 68 plus or minus 3 kilograms, were recruited from a daycare office. Neither of the subjects had a higher level of training background or any significance. They reported pain in the neck, shoulder, upper back, or lower back during the past year with a 10 centimeter visual analog scale. All subjects reported pain in one or more of the following body parts: neck, shoulders, and lower back, corresponding to an average pain recorded of 2.3 plus or minus 1.0. The project was carried out in the spring through March. Appropriate information consent was gained from the subject. The study was performed in accordance with the Declaration of Helsinki and approved by the local ethics committee, HC 2007-0033. Procedures. To attain valid and reliable information about levels of muscular activity during different types of levels of functional coordination training, the subjects need to be well familiarized with the exercises. Therefore, the subjects received instructions and practiced on the functional coordination exercises for 4 weeks before the muscle activity recordings were performed. The practice of the exercise consisted of 3 sessions of 20-minute durations per week. In figures 1A through G, the 7 functional coordination exercises with 2 through 4 levels of progression are illustrated. Level 1 is the most complex level of progression, with decreasing progression levels with numbers 2 through 4. That is the highest level of muscle activity. Was expected at level 1. 4 exercises, 4-point kneeling, prone plank, bracing, and bridge were performed in prone or supine laying body positions, and horizontal side support was performed in sideways laying positions, whereas Body blade exercises. And vertical plank were performed standing. The spine and neck were held in an anatomically neutral position with shoulder blades neutrally protracted during all exercises. Participants were instructed to activate relevant muscles all out for 20 seconds during static exercises and for 8 repetitions during dynamic exercises. The dynamic exercises were performed in an even and controlled manner with a pace of approximately 2 seconds per movement and in the following order: 4-point kneeling, levels 3, 2, 1, prone plank, levels 4, 3, 2, 1, bracing, levels 3, 2, 1, body blade, levels 4, 3, bridge, levels 2, 1, vertical plank, levels 2, 1, horizontal side support, levels 2, 1, body blade, levels 2, 1. The subjects rested approximately 1 minute between exercises. Bracing. Bracing was performed with subjects supine on the floor with the hips and knees flexed at 90-degree angles and the feet on the floor, and at 3 levels of progression, figure 1A. At level 3, subjects focused on stabilizing the trunk by activating the abdominal muscles. At level 2, subjects dynamically extended their arms to almost 180 degrees extension. At level 1, subjects dynamically flexed the hips at 90 degrees flexion so the foot was lifted from the floor. Bridge. The subjects were supine on the floor with hips and knees flexed at 90-degree angle and the feet on the floor. The exercises were performed at 2 levels of progression shown in figures 1B. At level 2, the hips were dynamically extended at 20 degrees while the subjects focused on stabilizing the trunk. At level 1, the hip and knee were statically extended to 0 degrees, lifting the foot from the floor. 4-point kneeling. The subjects were prone in a 4-point stand with knees hip width apart and hands shoulder width apart and hips and knees flexed at 90 degrees, figure 1C. The exercise was performed at 2 levels of progression, with level 2 was performed with no dynamic movement, only focusing on stability of the trunk and shoulders, while one shoulder and the contralateral hip knee were simultaneously extended in level 1, so the arm and leg were horizontally stretched. Horizontal side support. Horizontal side support was performed in 2 different levels of progression, as shown in figure 1D. At level 2, subjects were in side laying position with only knee and elbow resting on the floor. At level 1, subjects were in side laying position with only one foot and elbow resting on the floor. Prone plank. Prone plank was performed at 4 levels of progression as shown in figure 1E. At level 4, the subjects were prone with their knees and hands on the floor, shoulder width apart. At level 3, subjects were prone on their feet and hands. At level 2, subjects dynamically extended one hip to lift the foot from the floor. At level 1, subjects dynamically extended their shoulder to lift the hand from the floor. Vertical plank. Subjects leaned forward with their hands resting on the wall, shoulder width apart, and their body approximately 70 degrees to the floor. Figure 1F. Shoulders were 90 degrees extended. The exercise was performed in 2 levels of progression. At level 2, subjects stood statically in this position, focusing on stabilizing the trunk and shoulders. At level 1, subjects rotated their feet 90 degrees in relation to the floor and performed a bilateral shoulder abduction at the horizontal level, so only one arm supported the body against the wall. Body blade. The body blade exercises were performed in 4 levels of progression. Subjects stood on both feet hip width apart as shown in figure 1G. Subject stood with the dominant shoulder at 90 degrees flexed position holding a body blade classic NMK import bring Iviz 1B DK-3500 Verlos, Denmark. Horizontally in their hand at level 4. Small extensions and flexions of the shoulder were performed to make the body blade oscillate. Level 3 was similar to level 4 with both hands holding the body blade. At level 2, the body blade was held by one arm in a vertical position. Small abductions and adductions of the shoulder and horizontal level were performed to make the body blade oscillate. Level 1 was similar to Level 2, with both hands holding the body blade. Maximum voluntary contraction. To attain maximal levels of EMG activity for each muscle, isometric maximal voluntary contractions, MVCs, were performed in backward extension and forward flexion of the trunk and shoulder elevation in accordance to validated standard procedures. The subjects were verbally instructed and encouraged to slowly increase force, maintain a maximum level for about 2 seconds, and then slowly reduce the force. Each measurement of muscle strength was repeated 3 times with 30 seconds rest between, and if the force increased more than 5%, an additional MVC was performed up to a maximum of 5. Because of elevated blood pressures above 100 to 140 millimeters mercury, 3 subjects were excluded from the MVCs. Electromyography. Bipolar surface EMG electrode 6 millimeters diameter, Neuraline 725-01-K, Medicotest AS Rugenmarken 10 DK 3630, Ostke, Denmark, were placed on the skin with an intra-electrode distance of 2 centimeters of the dominant side according to standard procedures above the rectus abdominis, 3 centimeters lateral to the umbilicus. External oblique, 15 centimeters lateral to the umbilicus erector spinae, 3 centimeters lateral to the spine at the level of the cristae iliac, and trapezius, 2 centimeters medial to the midpoint between the acromion and the spinous process of C7. The reference electrode was placed on the spinous process of C7. The EMG signals were sampled at 1000 Hz data logger technology, HB Sweden, amplified, analog, bandpass, filtered 10 through 400 Hz, 8th order Butterworth, AD converted at 1 kHz and recorded on computer via a laboratory interface, CED 1401, Spike 2 software, Cambridge Electronic Devices, Cambridge, United Kingdom. The EMG amplitude was calculated by root mean square, RMS, with non-overlapping windows of 500 milliseconds. Start and end each repetition of all exercises were marked with a trigger. For the dynamic function coordination exercises, peak RMS EMG amplitude of each repetition was averaged from the first 4 repetitions of each exercise. The average of the first 4 repetitions of each exercises was done to get representative information of the maximum activity of each exercise. For static functional exercises, peak RMS EMG amplitude was averaged during the first half of the exercise minus the 2 seconds. The first half of the exercise minus the very first 2 seconds was used because of a very stable performance of the exercises in this part. During the MVCs, the peak RMS EMG amplitude with the time window of 500 milliseconds was calculated. Peak EMG mean SE trapezius 567.44 plus or minus 177.62 millivolts, erector spinae 103.63 plus or minus 25.9 millivolts, obliquus externus 95.20 plus or minus 11.43 millivolts, rectus abdominis 83.29 plus or minus 15.20 millivolts. The RMS and EMG activity from each muscle during the functional coordination training was normalized to the peak RMS EMG activity of each respective muscle from each respective subject during the MVCs. This was performed to attain the relative activity of each respective muscle during the functional coordination exercises. All tests were performed in the midday or afternoon, and the subjects were informed to eat and drink appropriately before the testing. The subjects were offered water during the testing. Statistical analysis. Analysis of variance for each muscle and Tukey-Kramer's post-hoc tests were used to test differences in muscle activation between the different exercises. For each type of exercise, only the progression level with highest muscle activity was applied in the test. General linear model was used to test the effect of level of progression. And Tukey-Kramer's post-hoc test was used to specify differences. An adjusted p-value of less than or equal to 0.05 was used as level of significance. Results are presented as mean plus or minus SE statistical analysis were conducted with an SAS version 9 SAS Institute Incorporated 100 SAS Campus Drive, Cary, North Carolina, 27513 through 2414. Because 3 subjects were excluded from the MVCs, the descriptive statistics on the normalized EMG activity were based on 6 subjects. However, all statistical tests were performed on absolute EMG values of the 9 participating subjects with within-subject comparison only. All difference of less than 15% between exercises was considered clinically insignificant. This was based on recommendations from general strength training literature, e.g. recommendations on hypertrophy 70 through 85% of 1 repetition maximum, RM, or muscular power 85 through 100% of 1 RM. Power analysis made before the study showed that 8 subjects in this paired design were sufficient to obtain a statistical power of 80% at a minimal relevant difference of 15%, a type 1 error probability of 1%, and assuming a standard deviation of 10% based on previous research in our laboratory. Results. Exercise type and activation above 60% maximum voluntary contractions. As illustrated in Figure 2A through D, the type of exercise had significant impact on the level of activity of the different muscles. Less than 0.05. The average activity of the muscles studied during the different functional coordination exercises is illustrated in Figures 3A through C. As illustrated in the figure, depending on exercise, the level of progression, all muscles reach the level of activation above 60% EMG max. For the upper trapezius, activity above 60% EMG max was reached with horizontal unilateral body blade 73.9 plus or minus 5.1%, and horizontal bilateral body blade exercises 84.9 plus or minus 7.5%. Erector spinae exceeded 60% MVC in 4-point kneeling, 79% plus or minus 11.7%. Horizontally bilateral body blade 77.7 plus or minus 8.1%. Bridge 76.3 plus or minus 6.3. Horizontal side support 71.6 plus or minus 10.2%. And vertical bilateral body blade 71.7 plus or minus 7.3. Obliquus externus exceeded 60% MVC in prone plank level 1, 124.2 plus or minus 24%. Prone plank level 2, 88.9 plus or minus 22.4%, and horizontal side support 64.9 plus or minus 7.8%. Rectus abdominis reached the 60% MVC level in prone plank level 1, 87.7 plus or minus 10%, and in horizontal side support 70.1 plus or minus 10.1%. Body position. For the erector spinae, the standing and sideways exercises resulted in a higher activity, 36.7 through 90.5 millivolts, in comparison with the prone and supine exercises, 19.2 plus through 71.8 millivolts. P is less than 0.05. Body position did not have any significant effect on muscle activity for any other muscles. Exercise level progression. The level of progression generally played a significant role for the level of muscular activity. P is less than 0.01, but based on the post hoc test, this was only significantly so for the trapezius muscle. For the trapezius progression of the prone plank from levels 4 through to 1, P is greater than 0.01, and 3 to 1, P is less than 0.01, significantly elevated the activity. There was a tendency to a difference between levels 2 and 1, P is equal to 0.05. Trapezius activation significantly increased from levels 2 through 1 of the 4-point kneeling, P equals 0.03. For the vertical plank progression from levels 2 through 1, increased the trapezius activity, P equals 0.01. For the body blade exercises, the different levels of progression provided different trapezius activation, in which level 4 provided higher activity than level 1, P equals 0.02. The levels of progression of the bridge, horizontal side support, and bracing, illustrated in 3A, did not play a significant role for the trapezius activity. Rectus abdominis muscle activity. By far, the highest activation of rectus abdominis was found during prone plank and horizontal side support, Figure 2A. Prone plank activated the rectus abdominis significantly more than the rest of the muscles except horizontal side support. Horizontal side support resulted in significantly higher rectus abdominis activity than the remaining exercises. Among the remaining exercises, no differences in rectus abdominis activity were found, but vertical plank provided the lowest activation. Erector spinae muscle activity. Bridge, horizontal side support, and 4-point kneeling resulted in the highest activity of the erector spinae. The activity during these exercises was significantly higher than in prone plank and bracing, figure 2b. Body blades showed a significantly higher activation level than bracing. Moreover, vertical plank showed a significantly higher erector spinae activation than bracing, providing the lowest erector spinae activity. Obliquus externus muscle activity. As shown in figure 2c, prone plank resulted in the highest obliquus externus activity, being significantly higher than all other exercises. The level of obliquus externus activity during prone plank was followed by horizontal side support, being significantly higher than the rest of the exercises except body blade. Between the remaining 5 exercises, no significant differences in obliquus external activity were found. Bracing through resulted in the lowest activity of obliquus externus. Trapezius muscle activity. As seen in figure 2d, the highest activity of the trapezius was found in prone plank and body blade. During these exercises, the trapezius activity was significantly higher than during bridge, horizontal side support, and bracing. 4-point kneeling resulted in higher trapezius activation than horizontal side support and bracing. Vertical plank activated the trapezius significantly more than bracing. The lowest trapezius activity was found during bridge, horizontal side support, and bracing, in between which no significant difference in level of muscle activity was found. Discussion. The main findings of the study were that untrained women can attain significantly high levels of activity in neck, shoulder, and trunk muscles for strength gain during functional coordination exercises. However, the activity of the respective muscles depend on type, body position, and level of progression the functional coordination exercises. A novel finding of the study was that muscle activity during functional coordination exercises depend on type, body position, and level of progression within each exercise. As we hypothesized, the type of exercise was important for the attained activity of each respective muscle of the neck, shoulder, and trunk. The significantly different activity of the recorded muscles during several of the functional coordination exercises illustrates the need for prescribing specific exercises for specific purposes. Therefore, the result of this study may be useful in designing specific exercise programs based on functional coordination training for populations with need for strengthening neck, shoulder, and trunk muscles in a controlled and functional manner. Because several exercises generate sufficiently high levels of muscle activity for strength gain in most of the recorded muscles, other considerations can be brought into play when deciding which exercise to use in an individualized clinic exercise program. For example, the exercise prone plank and horizontal side support provided very high activity of the abdominal muscles. The bracing exercise, which is also often applied exercise for the abdominals, generally resulted in low abdominal activity, 10 to 20% of maximal, and cannot be considered a strengthening exercise for untrained subjects. Exercises involving isometric muscle contractions without external resistance are earlier shown to generate insufficient levels of muscular activity for strength gain. However, the bracing exercise may still serve a purpose in the early part of training program, where the goal is to improve the ability to contract the muscles without an external resistance. For example, after cesarean section or other kinds of open surgery involving the abdominal wall. The normalized EMG data indicated that functional coordination exercises can activate trunk and shoulder muscles above the level required for strength gain in untrained workers with musculoskeletal symptoms. Although previous studies have shown improved coordination after coordination training, the present study indicates that this type of training can be used to stimulate gains in maximum strength capacity as well. This findings support that functional coordination training may be particularly appropriate for populations with high incidence of musculoskeletal pain and injuries, like workers with high physical demands or an athlete population. For example, the body blade exercise activates the often pain-afflicted erector spinae and trapezius muscles to sufficiently high levels for strength gain. Moreover, the high muscle activity of the trunk and shoulder muscles during the controlled functional exercises also indicates that they may be suited for injury prevention, rehabilitation purposes, and strengthening of the trunk and shoulder muscles for an athlete population. Previous studies evaluating activity of neck, shoulder, and trunk muscles during functional coordination exercises have shown correspondingly high levels of muscle activation as shown in the present study. However, these exercises were performed by younger or well-trained non-symptomatic subjects with a lower level of muscular activity, 45% of the maximal, considered necessary for gaining strength. Body position during the functional coordination exercises was of importance for the erector spinae muscle. The erector spinae was activated to a large extent during standing and sideways exercises than during prone or supine positions. This indicates that functional coordination training for improving strength in the erector spinae muscle may be most appropriate to perform in a standing or sideways position. Moreover, the level of progression during the functional coordination exercises was shown to be of importance for the attained level of activity of the trapezius, but not for the other recorded muscles. Traditional increases in level of progression in prone plank, 4-point kneeling, and vertical plank increase the trapezius activity. The level of progression with body blade exercises also played a role for the trapezius activity as shown in Figure 2. The unilateral horizontal body blade exercise resulted in the highest trapezius activity. A strength of the study was that the subjects were untrained women with musculoskeletal pain, and they were thoroughly familiarized with the exercises before the evaluation of muscle activity. A limitation of the study was that only sedentary women participated in the study, and the findings may therefore not be representative of a male or athlete population. Although the number of subjects may seem low, power calculations supported the number of the subjects provided a sufficient power for the analysis. The applied bipolar surface EMG with an intertrode distance of 2 centimeters provided only a few centimeters pickup area of muscle activity. This not only avoids significant levels of crosstalk from neighboring muscle, but also means that muscle activity from deeper muscles involved in the functional coordination exercises were not recorded. Practical applications. Depending on type, body position, and level progression, functional coordination exercises can generate sufficient levels of activity of neck, shoulder, and trunk muscles for strength gain. When taking the type, body position, and progression into consideration, functional coordination training may be a good choice for the prevention and rehabilitation of musculoskeletal pain and injuries, and an appropriate means for strengthening the neck, shoulder, and trunk muscles in a controlled and functional manner. The subjects practiced on the functional coordination exercises for 4 weeks for being well familiarized with the exercises before the testing of muscle activity. We would like to mention that the different complexity of the coordination exercises may provide different learning curves by all subjects learned to correctly perform all exercises within the 4 weeks of practice. Consequently, individually tailored functional coordination exercises may be well suited for both improving strength and coordination, and therefore be well suited for several populations with high incidence of musculoskeletal pain and injuries.